difficult questions, I would be delighted to answer them to the best of my knowledge. Having said that, I would like to start by saying that this is a subject in which the last words have yet to be written. They are, as my dear friend and fellow climate change analyst Navroz Dubash mentioned, this is a wicked problem. A wicked problem in as much as the problem itself, to define the problem itself is difficult. Much, much more difficult is it to define the answers. And then it is at various levels and various sectors. So this is a problem that is all over the place. What I will do today is share my thoughts with you and I put a presentation together. And once in a while, and let me share my presentation, once in a while in the presentation, you will see a page which has, in my view, the lessons that I have learned written on it. It would be great if we go through those lessons, and the other slides are essentially building up on why I believe that that is a lesson. Okay, there you go. So this is the first lesson, and this goes to the central point of why is climate change important? Why should we consider it in public policy? And the point simply is that climate change is one intervention which threatens our well-being and the well-being of all people across the world, irrespective of where they are, whether they are in Russia, which believes that things will be better for it because areas which are non-arable become arable because of a warmer climate, or whether you are in India or the Maldives, where you expect a lot of water-related changes to influence how we do agriculture, how we look at sea level rise. And the rich countries obviously have the money to be able to solve the problem, or at least keep the adverse impacts at bay. But for poorer people, even in the developed countries and developing countries where there are low resources to begin with, it is especially difficult. What are these problems? The first, of course, is increased temperatures. And increased temperatures, for example, in Surat, means that there are a larger number of both heat strokes as well as deaths due to increased temperatures. It also means that the productivity of agriculture falls, whether our two main cereals are wheat and rice, and both of them have a peak yield temperature. And if you are beyond that peak yield temperature, the peaks start falling. So there's an inverted U kind of thing. The second impact is fewer rainy days, but on those days when it does rain, there's a higher precipitation. This is something that the Indian Institute of Tropical Meteorology is finding in India even now. This was predicted by the climate models as early as 20 years ago, that this would happen in the Indian subcontinent. But we are seeing this, that the total amount of rainfall hasn't appreciably changed over the last 30 years. But what has changed is the number of rainy days. They are much fewer. And consequently, when it rains, it pours. And this leads to all kinds of problems, including the increasing numbers of cases of urban flooding that we have been seeing in the past few years. It also means that when it rains, there's a lot of water. And if we don't have enough storage, and as a country we don't have enough storage, the water then flows away and flows away ultimately into the sea. It means that the amount of reservoirs that we have, the amount of storage we have, needs to increase. But in a densely populated country, it's a challenge. The third issue is that all our rivers are fed by glaciers. And as the temperatures rise, the glaciers melt, it increases the amount of flow in the rivers. But once they're melted, that river flow decreases. So whether it is in the short term, a year, during the course of the year you have more rainy days, or it is a longer term of decadal timeframes, you've got higher and then lower water flows. So this volatility in water flow is something that we are beginning to see already as an impact of climate change. And this obviously has huge impacts on, for example, how do you do agriculture? When you expected rain to occur and it didn't occur. The last issue is the increased intensity of cyclones. And this is true across the world, whether you look in the Indian Ocean at the cyclones which hit the eastern coastline, or you look at the cyclones in the Pacific or the cyclones in the Caribbean, all of them. What we are seeing is that with increased temperatures, particularly of the oceans, the amount of evaporation increases, and therefore the intensity of the cyclones increase. The number of storms which convert into cyclones has dramatically increased in the past 10 years. So in the Caribbean, where this is the most intense problem, the increase in storms to cyclones has gone up from about 30% to about 50%. And you notice the intensities which wiped out complete islands a couple of years ago. This obviously implies that people have more erratic incomes because you don't know whether the season is going to be good. You can have agricultural produce. 70% of the people in our country live on agriculture. And it also leads to greater income inequality. If you look at people who depend on natural resources, because of this erratic nature, their incomes fall. And because of that, what we see is that the people whose, like largely you and me, whose incomes depend on non-natural resource-based activities, their incomes keep steady, while those who are dependent on natural resources, their incomes fall. So these are both the physical and therefore the economic impacts of climate change. This is a serious issue. It affects everybody in the world. And as you can see, if you are poor, you're going to be hurt a lot more than if you are not. So this therefore becomes a challenge for us. There's a certain amount of carbon dioxide which is already in the atmosphere. If it's already in the atmosphere, there is some amount of climate change which has already happened, even if we bring all the greenhouse gas emissions down to zero today. So there is an unavoidable climate change that we face, and managing it is important. But the greater issue is that we have to ensure that the amount of carbon dioxide emissions or the greenhouse gas emissions in the atmosphere don't keep on increasing. Because if they do, then we will go beyond the point of irreversibility, and then we have unmanageable climate change, or runaway climate change as it's called. So a key challenge today for everybody in the world is to avoid unmanageable climate change. So managing the unavoidable and avoiding the unmanageable is our goal as we move ahead. It's the goal of every country. For some, managing the unavoidable is more important. But for all, avoiding the unmanageable is also important. So how do we do this? As far as managing the unavoidable is concerned, which means that the climate change that has already happened, we talked of the impacts when we were in a moment ago. So what do you do? So we look at better seeds. We look at crops which have got peak yield temperatures which are higher. We look at enhancing water storage, and we look at avoiding the loss of food, and therefore food processing infrastructure becoming better. As far as avoiding the unmanageable is concerned, which means reducing the amount of carbon emissions that we do, I think it is largely around enhancing energy productivity so that the amount of energy that you need is less. Why am I talking about energy? Because the largest amount of greenhouse gases that are produced, the climate change gases, 70% of them come from energy-related emissions. When we burn fossil fuels, we produce carbon dioxide. And that is the most potent of the greenhouse gases that is out there. So first, you reduce the amount of energy needed. So for example, if you have a more efficient air conditioner, provides the same amount of cooling, uses less energy. That's enhancing energy productivity. The second is, whatever energy we do need, we provide it through renewables. because renewables do not have a carbon dioxide emission as fossil fuel use does. The third is let's use electricity, because remember we are moving towards renewable electricity. Let's use electricity everywhere. For example, in automobiles, today we are using oil, fossil fuels. And tomorrow, if you use electricity, then day after tomorrow, when all the electricity is renewable, you've got a transport system that's based on zero carbon as well. And the fourth is that we restrict the global temperature rise to less than 2 degrees centigrade, preferably 1.5 degrees centigrade. Those are the key challenges that face us in avoiding the unmanageable flow of greenhouse gases. So let's delve a moment into the politics of this. As we look into the politics of this, we have mentioned that in most countries, in most of the developed, the richer countries, the impacts are important, but they are not as important because they have the resources to be able to cope with them. In India, on the other hand, strengthening resilience is very important. And as we make new waterways, as we do enhance our health systems, we need to build them to not only take care of today's problems, so whatever is the shortfall, but also to additionally ensure that they don't go down under the impacts of climate change. So if you're building a reservoir, that reservoir has not only to be large enough for today, it has to be large enough for tomorrow when we have a greater volatility because of the water availability or volatility in water availability due to climate change. But I would want to focus on one particular issue, and that is that in our countries, the developing countries, energy use is still low. Enhancing energy use and making sure that everybody has got adequate energy is important. As a rule of thumb, the amount of energy that the OECD countries use, the lowest amount of energy that any OECD country uses, and that's Japan, they use about 4 tons of oil equivalent worth of energy per person per year. Now, 4 tons of oil equivalent is whether it's electricity, whether it's biomass, whether everything combined, you put it into one metric, which you define as a ton of oil equivalent. So 4 tons of oil equivalent is the absolute minimum that these countries use. Where is India? India, we are barely able to supply approximately 1 ton of oil equivalent worth of energy per person per year. And you see this. You see that the amount of energy that people use is low. So obviously that energy has to increase. If we want to move, if we have the aspiration to move to a quality of life, which is similar to those in the developed countries, in the OECD countries, there is no way we will be able to do it at the current energy levels. Now, it is quite possible that with energy efficiency, the 4 tons oil equivalent per person reduces to 3.5, possibly even to 3. This is the kind of change. This is what we talked about, that the productivity, energy productivity has to increase. But we are still looking at 3, which is 3 times where we are today. So we are looking at a huge amount of energy increase. But if it is all based on fossil fuels and there's carbon emissions occurring, we'll end up frying the planet. So for us, the challenge is that we enhance people's incomes, we enhance people's livelihoods. Our goal is that India has a quality of life which is similar to that of an OECD country. We believe that increasing energy use is essential, but at the same time, we do it in a manner that we do not produce the same amount of carbon dioxide emissions. So those are the challenges that we face. And our challenges are very different from the challenges that the world faces. And you see this in the climate negotiations, where the agenda of the developed countries is largely around how do I manage what I have. I want to move to renewables, but I've got enough fossil fuel capacity for enough electricity to the country. I've got enough oil to power all the cars in my country. I need to move from fossil fuels to renewables. In India, you're looking at an expanding pie. The pie is this big, it will become much larger in the years to come. And consequently, working with an expanding pie becomes, I believe, a greatest challenge, and I will argue also an opportunity for us. So now that we have got this global challenge, how much is the time that we have? There are umpteen models which look at carbon emissions and the carbon dioxide levels in the earth and the kinds of temperatures that they would result in. And what we did was we looked at all of those, and there are, I don't know, something like more than 50 of these things, and looked at the ones which allow us a future which is consistent with approximately the 900 million ton carbon emissions that we can still have between 2015 and 2100, and see how this works out. And these are the two extremes. The first one sees us going to zero carbon dioxide in 2050 and remaining there. The other one sees us going to 2070, but then it is going to a negative one, which means that we will have to remove a lot of carbon from the atmosphere. And this is what in the literature are referred to as negative carbon technologies. What is a negative carbon technology? We know forestry, but people then talk of technologies that can capture CO2 from the air and so on. Amazingly expensive. I would much more argue for a scenario A curve, which is looking at going to zero early, than one which allows us to produce carbon emissions late, but then invest a huge amount of money in these negative carbon technologies. So between 2050 and 2070 is the time period that we have. We are at a moment in history where making this happen, therefore, we are in 2020 or 2021 now, we have 30 years, at the most 50 years, but probably 30 to 40 years to be able to do this. So time is of the essence. I will argue, why is this of the essence? Whenever technological changes have occurred in the past, and if you look in the literature, these are called long-term Kondratiev cycles. They typically, for this kind of change to occur, there are 70 to 100 year cycles. That's the time it takes. Here we are talking of 30 to 50 years. So it is a halving of the amount of time that has taken humans in the past when we moved from coal to oil or oil to gas. So this is a global challenge which faces all of us. How much would we have to do? Well, I'm kind of jumping ahead a little bit. I'll come back to the Paris Accord in a moment. But one of the things that the Paris Accord did was each country said what is it that they can do. They produced what was called the Intended Nationally Determined Contributions, or INDCs. And if you added up the INDCs of the world, what we see is that the global emissions would be more or less stable and reach about 52 gigatons of CO2 equivalent in 2030. Is that enough? No, it is not. And we will come to that question in a little while. But just to give you a flavor, the countries in the world are looking at a 10-year horizon now, in which we are looking at the global emissions being more or less constant. Now, as I said earlier, the vast proportion of carbon emissions are related to energy generation and use, whether you burn coal or gas for electricity generation, whether you use petrol or diesel in running cars and trucks and two-wheelers, whether you use coal in industry or whatever. This is where the vast bulk of carbon emissions are coming from. Now, I have found it useful to use a four-step process on moving ahead towards a zero carbon energy future. The first is, of course, energy efficiency. Enhance energy productivity so that the amount of energy that we need reduces. And this is what I was saying, that instead of India becoming a OECD country using 4 tons of oil equivalent of energy, we do it at something much less, possibly at 3. This has happened in the past. When the US and the UK industrialized, the technologies that they used at that point of time locked them into into energy use of 7 to 10 tons of oil equivalent per person per year. By the time Japan and Korea industrialized, there were more efficient technologies available, whether it is for transmission of electricity, whether it is for generation of electricity, whether it is for the end use, houses and so on, cars and so on. As a result, Japan and Korea use about 4 tons of oil equivalent of energy per person per year at the same levels of the Human Development Index as the US and the UK. So energy efficiency is obviously important. The second is the largest amount of emissions come from the conversion of coal or gas to electricity. In India, it's largely coal. In many other countries of the world, it's gas. But if we can move this towards a zero carbon substitute, then a very large part of the problem, something like 60% to 70% of the problem, is solved. Is this happening? Yes, it is. So today, in the latest auctions carried out by the Solar Energy Corporation of India, the price of renewable electricity, the price of solar electricity, was 1.99 rupees per unit. 1.99. This is the cheapest electricity available in India from any source, but it's only available when the sun is shining. Now, unfortunately, our largest demand for electricity occurs at 7 p.m. to 11 p.m. and there's no sun at that time. And coal is the cheapest electricity at that point of time. So right now we are in this strange situation where you have a great acceleration of renewable electricity and an acceleration of coal electricity as well, because energy demand is increasing. Will this happen forever? Well, that depends on storage technologies. Because if I can produce electricity during the day from solar, store it, for example, in batteries, and make it available to you and me at night at prices that are competitive with coal, then we are good. Why do I say prices that are competitive with coal? Remember, a lot of people in this country still cannot afford to use electricity because of its price. We cannot sell high cost electricity. We need to ensure that the electricity that we sell is at a price which people are willing and able to pay. Consequently, ensuring that the prices of renewable electricity that we provide are at least equal to, if not less than, the price of coal electricity is important. I think we are nearly there. Again, in a tender carried out by the Solar Energy Corporation of India, I think in April or May this year, during the lockdown, found a price for round-the-clock renewable electricity, that's solar plus batteries, at a price which is comparable with coal-based electricity, to be delivered 2 years from now. So it's quite possible. Well, it's already 1 year, so say a year and a half from now. So it's quite possible that a year and a half from now, we will have renewable electricity supplying us electricity round the clock, either directly or from batteries, which is competitive with coal electricity. And beyond that, there would be no need to build any more coal power plants or coal mines. But that's still in the future. The third point, which I said earlier, was wherever we can, let's substitute fossil fuel use by electricity, because electricity is moving towards renewables. And if, for example, for cars or in industry where we are using coal, can we start using electricity? Will this happen? Well, yes and no. We'll come back to this question in a little while, because battery buses have shown to be less expensive, and several cities in Delhi are going for in India are going for battery buses. It is also the case with two-wheelers, and there are 6 times as many two-wheelers as cars in India. They use about 3 times as much petrol and produce 3 times as much as CO2, two-wheelers, as compared to four-wheelers. So even with two-wheelers, the case has been made, but now the issue is how do we scale it up and move it much faster. But there will be cases where we can't use electricity. For example, if you've got trucks which are going long distance, what do? The weight of batteries is so much that it takes away the payload that a truck would use to carry goods. If I'm using aeroplanes, how do I use? I don't know. If I'm making cement, there is calcium carbonate, which is calcined into calcium oxide. CO2 is produced. I have no idea of any other chemical process through which I can make cement. So these are areas where we are stuck with, electricity won't serve the purpose. So what do? And therefore we are looking at a range of fuels which are zero carbon, hydrogen and biomass fuels in specifically, to use where electricity cannot be used. So this is the kind of strategy that I think most countries are putting into place. Different countries are at different levels of implementation. I would just point out that it is extremely important that the per capita energy use changes very fast, particularly in the OECD economies, and in the non-OECD economies like India, it remains constant at the level that we are, or becomes slightly more and then levels off. Because without doing this, we would not be able to reach the other goals that we looked for. The total amount of solar energy, the total amount of storage would be so huge that the planet would not be able to sustain it. So now the challenge is, how do we go ahead? We discussed this a little bit. We said that the energy generation and use infrastructure in India and most developing countries is yet to be built. Can this be built on a low and zero carbon option? But didn't we just say that it depends on the ability and willingness of people to pay? And if this is more expensive, how will this happen? Aha! So the challenge is, how do we bring down the price of the low or zero carbon option to be less than that of the fossil fuel option? Example, renewable energy in India. Renewable energy in India, as I said, solar energy already costs less. We have broken one barrier. The next barrier is, even at 11 o'clock at night, it should be the cheapest form of electricity. We expect to break that barrier in about 2 years. So today, approximately 25% of applications where carbon emissions are produced, in those applications, zero carbon technologies are already cost effective. We therefore need to work on technology, of course, policies, how they are priced, because if something costs high upfront but costs low later, you need a pricing strategy that can help level out. All of you are familiar with the EMI concept. How can we get EMI into these kinds of energy interventions? And for that, financing is important, because depending on whether a bank finances you for 3 years or 10 years makes all the difference in the world, because the interest burden therefore becomes spread over a longer period of time. And the last thing is business models. This is to a certain extent dependent on pricing, but if you and I can purchase something in a business model that has got an EMI attached to it, we are a lot more likely to buy that low carbon emission than if we had to pay all the cost upfront. Nowhere is that better seen than in the case of battery buses. Battery buses today, as I said, actually cost less, but on a lifetime basis. Their capital cost is more. So if cities have to buy a bus, they'll be able to buy fewer buses. But supposing they rent a bus from somebody else who gives it to them as a service. So in Delhi, for example, CNG buses are leased. It's called the kilometer scheme, KM scheme. And we pay 60 rupees a kilometer. Interestingly enough, in Delhi, if I source electric buses and pay them on a per kilometer basis, the price which people are willing to accept is less than 60 rupees per kilometer. In other words, there's no rationale now for going in for CNG buses. And several cities in India, Calcutta, Chennai, are going in for large scale development of electric buses. Let us now come to the Paris Agreement. This is something on which a lot of you have set a lot of questions, and I hope I can do some justice to this. I think the Paris Agreement is important because of two reasons. The first, of course, is that it's the first time that the world as a whole decided what our goal would be. We said there is no way we will let the temperature of the world be more than 2 degrees centigrade above the pre-industrial levels, but preferably closer to 1.5. This was a big deal. The second was that the Paris Agreement says that instead of having top-down approaches, which are difficult to control, when countries find that they are not meeting their top-down goals, they just walk out of the agreement, as happened with many countries in the Kyoto Protocol. So there's no sanctity to goals that are allocated. On the other hand, countries are told, you say what you can do. Now, if I have said something, the chances that I will meet it are high. That makes me confident that the next time around I can pledge a larger target. It also brings up the trust in other countries that you, India, will deliver on your target. So it creates a virtuous cycle of trust and confidence. This is the principle around which it is based. Consequently, the whole goal is that in whatever development you do, climate is the new paradigm. You take climate into account whenever you are looking at a development. Now, as a result of the Paris Agreement, the countries had put in their nationally determined contributions, their NDCs. And when you look at that, and this is the third box from the top, unconditional NDC case, we look that the goal of the world is that by 2030, we should be in the 55 gigaton range. But if we want to be at 2 degrees, we should be 42. If we want to be 1.5, we should be at 36. So there's still a large gap. It's often called the 13 gigaton gap because people are talking of 2 degrees, or it could be a 19 gigaton gap if you're looking at. So yes, we are moving in the right direction. In 1995 or 97, when we did the global baselines, we saw that in 2030, the emissions would be 65 gigatons. As a result of that, countries changed their policy trajectories. And today we expect that with our current policies, we will be at 59, already a reduction of 6. And then countries have promised that they will do more things, which bring us down to 55. So what I will request you to focus on is the point that over a period of time, the global world goals have declined from 65 to 59 to 55. And our goal has to be that we are able to move closer to somewhere in between the 36 and 42 gigatons. So I will leave you with the thought that global negotiations probably help more in informing all the countries that this is a genuine problem. That's number one. Number two, that everybody is doing something about it. And number three, actually it makes sense for me to move in this direction. So it influences their policy, and their policy then influences the discussions. And I think this feedback loop has been very effective in enabling the lowering of the emissions that we expect to happen in 2030. As I said, if all the countries do what they have promised in the NDC, they still will not meet their goals. And therefore, the Paris mechanism has what is called a ratcheting up of ambition. Periodically, and this will happen in 2024, countries of the world will get together in what is known as a global stocktake. We will see where we are. What are the kinds of emissions that are happening, and therefore how much more needs to be done. And look at the prices of technologies, the level of their performance, and therefore look at the kinds of opportunities that exist. And that hopefully would lead to countries adopting more stringent NDCs. By the way, and I'll come to the Indian NDC in a moment, when we thought of that NDC in 2015, it was a tough one. And I'll just show you a graph on it. It now seems that by next year, by 2022, we should be able to meet it. This is how quickly technologies change, how quickly performances change, how quickly costs change. At Paris, this pledges, this ratcheting mechanism was accompanied by the creation of two global technological cooperation scenarios, because it's clearly seen that technology is what will make this difference. One is the International Solar Alliance, and the other is Mission Innovation. And as the name suggests, it is about promoting solar across the world. It is about creating innovative technologies that look at lower carbon and zero carbon technologies. Now, at this point of time, I think it is important to look at cost trajectories, because at the end of the day, the reason why renewables are going on is because prices have come down. When we went to Paris, we could already see that. We had already also seen that in the case of LEDs, where when LEDs came in, they used to cost 500 rupees a bulb. Even at that price, it paid for itself because of its saving in 3 years. But did we use it? Did I use it? No. But then we started off creating a market for this. Hundreds of thousands of people would buy it. Millions of people said, we want to buy it. And we created a special company, EESL, Energy Efficiency Services Limited, which went out and got these bulbs in bulk. The first time they got it, when the price was 500, we got it for 310 rupees. We were ecstatic. But the next time it was 240. The next time it was 190. And the prices kept declining till the sixth time the price was only, I think, 47 rupees or something. This tells you the power of volumes and to both reduce costs and enhance performance. And it therefore tells us that while the initial costs are higher, the initial cost of a LED bulb are still much higher than that of an incandescent bulb, but the running costs are much, much lower. So if we looked at renewables and if we look at 24-hour electricity, we still see that the long-term cost of electricity is higher because battery costs are still higher. Therefore, technology evolution becomes important. How do you ensure that technology evolution occurs? And in a way that performance increases and prices decrease. This is today the central question around the acceleration of our climate goals. So coming back to India's goals. So when we put our goals in 2015, we were looking at seeing one of our goals was that the carbon intensity of our economy is 33 to 35% less than what it was in 2005. So this tells you where we are. So we would go from carbon emissions of about, they were less than 2 billion tons in 2005. In 2015, they were still something of the order of 2.8 billion tons. We would have gone to 11.4 billion tons, but instead we said we'll go to 7. As I said earlier, we seem that in 2 years we will be at the 7.4 mark. We will probably reach 2030 by being at the 6.5 to 7 billion tons instead of 11 billion tons as we had thought. Now this is important because what it tells us is that as technologies have developed, the uptake of new technology, in India, uptake nearly doubles capacity every 6 or 7 years. So it is said that the amount of buildings that we will have in 2030 will be more than double. Some say they will actually be 3 times the amount of buildings that we have today. If each of those buildings is more energy efficient, if each of those buildings is zero carbon, you can imagine the kind of impact it has on this curve. And that is what is happening. And consequently, specs regarding the kinds of energy generation and energy use technologies for tomorrow become important. If each air conditioner sold tomorrow is more efficient than the air conditioner sold yesterday, if each electricity generating plant is lower carbon producing tomorrow than it was yesterday, then we are on the right track. And it seems that we are. In the INDCs, we looked at 8 levers, out of which 6 were quantified. We said that non-fossil fuel electricity would be at least 40%. We said that the carbon intensity would be 33 to 35% less than in 2005. And we said that the amount of sequestration that we do from forests and tree cover would be an additional 2.5 billion tons of CO2. In these 5 years since the Paris Agreement, we are already 25%, as I said earlier, 25% of carbon emissions already have zero carbon emissions that are cost effective. And we'll be probably at 60% by 2030. So the point that I want, and none of us thought this in Paris. In Paris, it was thought that in the electricity sector, we would still have coal-based power plants, and we would have something called CCS, carbon capture and storage. As the emissions come out of the coal-based plants, they have CO2 in it. You capture that CO2 and you push it underground, which adds a huge amount, almost 25% to the cost of electricity. You can imagine that we did not like it. Now, with renewables, you've got electricity which is cheaper and you have no needs for CCS. CCS has disappeared from the electricity agenda. It is still needed for things like cement, which I talked about earlier. The calcium carbonate going to calcium oxide produces CO2. We don't have any technological solution. Maybe CO2 capture is the only way to go ahead. But just imagine from the whole of the electricity sector to only the cement sector. What a technological advancement these 5 years have brought. I'm going to spend the few last minutes on India. Now, if we look at what is happening in India, we looked at the supply side transition. And what we see is that by 2030, approximately 46% of the electricity that is generated and about 64% of the capacity would be renewable. We have promised 40% in our Paris agreements, that 40% of the capacity would be non-fossils. It will probably be somewhere nearer 64, 65%. This would also address local air pollution problems. But remember, this does not mean that coal goes to zero. The existing coal continues. It is only the additional capacity that becomes renewables. So we will need to address air pollution as far as coal is concerned. We will need to ensure that the coal-based electricity can ramp up and ramp down. More on it in a minute. And we will need to ensure that we have got balancing systems. So hydro in the short term. You remember during lockdown when there was a time when we said we'll all switch off our lights. And at that point of time, the way we managed it was through hydro. We ramped down hydro. We went to as much hydro usage as possible. We ramped down hydro to bring it to zero. And then we ramped up hydro to bring it back to the kind of usage. So you need these kinds of things to help the ramping up and ramping down of variable renewable energy. You also need things like battery storage in the future as they become more cost effective. So what we are looking at is today the price is about 9 rupees when you're looking at solar plus battery. We are looking at a technology learning, which is essentially scale, which leads to a reduction of 3.5 rupees. We are looking at cheaper finance, which means that the rate of interest becomes less, and it reaching about 4.8 rupees by 2030. And 5 rupees is today the current cost of new coal power plant electricity with all the required air pollution equipment built in. This implies that we are on the right track. Now, clearly, what it also means is that technology learning is crucial. And therefore, learning from international markets, creating the kinds of skills and opportunities for these technologies to develop becomes important. The last point that I wanted to touch was on hydrogen. We have traditionally used hydrogen in the refineries and in fertilizers. And we have got it from treating gas. That comes to hydrogen at about $2 per kg. We are looking in the future at a much larger use across a range of sectors. But what it means is that prices will have to decline as well. And if we are looking at green hydrogen, then we have to look at how green hydrogen is water electrolyzed to make to split renewable energy to split water. When we looked at various end uses, we found that it actually doesn't work in EVs unless you're going for long routes. But for others, we would be competitive if we can bring the price to below from the current level. If today you use PV to split water, it is about $5 per kg. But as the volume increases, the price comes down and these new markets open up. Then the prices go down further. Then a new market opens up. Then the price goes down further. And therefore, we do now have a game plan on ensuring that we are able to move into new markets using electricity. So let me end by focusing on what I think are our key learnings from this exercise, from these years. The first is that this climate change is a huge challenge, particularly for a poor and densely populated country like India. For us, the energy transition makes sense. We can't depend on imported energy, and using local energy in a cost-effective manner clearly has an interest. We have ambitious policies, and I think the challenge is therefore how do we bring in the policies that create the demand for the newer zero carbon technologies. We have been successful in LEDs, we have been successful in renewables. We need to move similarly into electric vehicles. We need to move similarly into industry, into hydrogen, and so on. If you ask me, the key challenges that we face are, one is this grid integration. You've got more and more variable renewable energy because sun happens when the solar happens when the sun is up. Wind happens when the wind is blowing. And that has to be in the grid. When you put on a switch, you want electricity to flow. Uh, EV infrastructure is important. Charging infrastructure is amazingly important. I think that is one key input that would help take off for the EV revolution to take off, particularly as far as two-wheelers and three-wheelers are concerned. The industry transition. How do we reduce material demand so that you can use the amount of renewable electricity that is needed? And finally, for hydrogen, green hydrogen, how do we create the processes so that there is an increasing size and increasing costs, as we just discussed? So therefore, I would like to end with with the suggestion that I believe that we are on the right track. I believe that it is possible for us and for the world to go into a near zero carbon future by 2050 to 2060. And I believe that creating policies within various sectors that I spoke about for increasing demand is the best way to accelerate the process. I want to thank all of you, and I think we still have some time. I spoke longer than I thought I would, but we still have some time, and I would love to have any questions which I have not already answered. Thank you very much. Let me take down the presentation.
Thank you, Dr. Mathur. Dear students, if anyone has any questions, please raise your hand and I'll unmute your mic, please.
I hope my thing is unshared now. Yeah.
We can still see your presentation.
Oh, you still can. So I will need to look at the shared window. I hope it's okay now. Okay.
Yes.
Go ahead.
Okay, I think students are maybe shy.
My suggestion is, Professor Velanki, if we can take 2 or 3 questions, and let me see how much I can answer in the time that we have.
Okay. Dear students, you can type your message or the question for Dr. Mathur here, and and Dr. Mathur will answer 2 or 3 of the relevant questions, please. Okay, Dr. Mathur.
Yeah.
Okay, now we have a couple of questions, Dr. Mathur.
Is there a way I can see the questions? I don't see a chat box, but anyway, Professor Velanki, why don't you tell me the questions?
Sure. Ayan Shri, can you unmute and talk to Dr. Mathur, please? Ayan Shri.
Yes, sir. Good afternoon, sir. Sir, my question was that when we talk about shifting to electric vehicles and electricity, but I was reading an article where it said that lithium extraction, or for that matter, silicon extraction, has a lot of carbon emissions of its own. So won't that also be a challenge?
Anybody else? Yeah, go ahead.
Sir, your mic is muted.
Yeah, is there anybody else who has a question, or should I just answer this?
Yes, please. Mr. Apurva asks you if we can move towards using hydrogen fuel in the near future. And then Sadak Gupta asks about lithium-ion batteries as proposed by Tesla. Are they a reasonable solution for the grid-scale energy storage, considering the relevant issues that you mentioned? And Daksh, since the time the talks began to came to light over the issue of climate change, there has been a rise in critics questioning the nature of science or climate change. So how does one counter such kinds of criticism not based in science? I think that should be enough for the time we have, Dr. Mathur.
Thanks. Thank you very much. Very, very quickly. Your question about the carbon emissions from the extraction of lithium and silicon are very, very well taken. But supposing tomorrow we have a economy in which the grid electricity itself is based on silicon. So therefore, yes, in the medium term, the silicon would be mined by electricity which has got carbon emissions. But in the longer term, it would be mined by electricity which is carbon free. So at that point of time, there would be no emissions. So I think this is purely a matter of time. And my own expectation is that by the year 2040, you would start seeing large scale mining which is carbon free. The second question was on hydrogen. As I mentioned, currently in India, hydrogen made from photovoltaics used to split electricity is about $5 per kg, and that made from gas is about $2 per kg. But even today, there are opportunities where hydrogen can be used. So for example, we looked at the SME clusters in Howrah. Wherever diesel was being used, you could close your eyes, have a small electrolyzer with PV panels. You're not transporting hydrogen over long distances, and use that hydrogen instead of diesel. It makes cost effective sense today. Now, as you would expand this, the markets would expand, prices would fall. The next market that would open up would be that of a range of industrial uses. Apart from diesel, it would then start moving into coal and so on. So that is, I think, the way in which hydrogen fuel can be used. As I said earlier, hydrogen is used in large scale in ammonia and refineries today. There's no reason why it can't be used in other cases, especially because instead of large generating systems, you can have smaller generating systems. The third question was on lithium-ion batteries and whether grid scale is possible. Yes, it is. In Delhi, the Tata Delhi distribution company has put up a 10 megawatt battery facility, which it uses to smoothen out the frequency variations that occur. It's been operating for over a year and a half. And I think as battery prices go down, you will start seeing more and more of such installations. In Calcutta, the utility is looking, and we are working with them on setting up batteries in very densely populated urban areas instead of adding new transformer capacity, because there's no space for new transformers. So you put a battery. When the transformer is not at 100% capacity, the batteries get charged. When the transformer is at 100% capacity, the additional electricity is drawn from the batteries. And tomorrow, these batteries could be charged from rooftop solar that is built up there. So we are seeing all kinds of interesting interventions, interactions between the grid. The last question was on challenging the science. So, I have two answers to this. Neither one of them is completely right, but they work together. The first is that the number of people questioning the science has decreased dramatically. Between the year 2000 and now, the number of mainstream players who question climate science is much, much, much less than what it was. And therefore, in a certain sense, there is a natural dying out of critics. That's one part. The second part is that the science which these people question climate on, we are getting more and more answers to it. So the scientific space that is there for critics keeps shrinking. So there was this issue of how does water vapor behave? What is the background radiation? Those questions have been answered. And therefore, the space keeps shrinking. So between these two, the critics themselves shrinking, the numbers of critics shrinking, and their scientific argument shrinking, we are seeing the critics being, in a sense, answered by them, by their own demise. So Bhanu, thanks very much. I also see Professor Gurjar is there, Professor Padhi is there. To all of you, very many thanks.
Yeah, I mean, sorry to intervene.